Continuing our discussion in section 1.7, let's look at a couple more examples of solving word problems. First, let's look at some mixture problems. The manager of a Starbucks store decides to experiment with a new blend of coffee. She will mix some of the B grade Colombian coffee it sells for $5 a pound with some A grade Arabica coffee that sells for $10 per pound to get 100 pounds of the new blend. The average selling price of the new blend she wants to be $7 a pound. There is no difference in revenue between selling the new blend versus selling the other types separately. So how many pounds of the B grade Colombian coffee and how many pounds of the A grade coffees are required? So the first question you always ask is, what are we trying to find? And right here, the last question, the part with the question mark, says, how many pounds of B coffee and how many pounds of A coffee are required? So right here, we want to find how many pounds of A coffee and how many pounds of B coffee. So we're going to have to mix A coffee with B coffee, a certain number of pounds of each, to create 100 pounds total. And we want to know how many pounds of each we want to mix together, so that way it comes out to $7 per pound. So first, let's define our variables. Okay. In this case, let's let C equal the Colombian coffee, or in this case, I guess we could have said B for grade B. That would have worked too. Let's let C equal the grade B Colombian coffee. Again, it doesn't matter if I would have done starting with A, I could have done that as well. Okay, so we're looking for how many pounds of that brand of coffee. Now, we don't want to create a different letter for the other coffee. Okay, the other one is going to be how many pounds of grade A. And this will also be in pounds. So again, we don't want to create a whole different letter. We want an expression involving the letter C, just like we did on the last example with the last video. Well, we know we total want 100 pounds, right? So we know that whatever we use for grade B coffee plus however many pounds from grade A coffee needs to total 100 pounds. So we know that grade A coffee then is going to be 100 pounds minus however many pounds we took from grade B coffee. So we're going to let grade A coffee be 100 minus C. Okay, so we have C is going to be the pounds of Colombian coffee, and then grade A coffee is going to be 100 pounds minus whatever we used here is going to make up the balance. Now, what are the facts from this question? We know that the grade B, okay, let's put grade B here. We know that it sells for $5 per pound. And we know that grade A coffee normally sells for $10 a pound. So it's obviously a more expensive coffee. We know we want both of them. We're going to add these together. And we know we want a total of 100 pounds of coffee. And we want it to equal $7 per pound. So we have to come up with some sort of an equation using all of this information, but I haven't even entered in my variables yet. I just know that both these coffees are eventually going to add up to 100 pounds, which is at the $7 per pound mark. To give you a quick picture, I already drew one here. Again, we have the grade B Colombian coffee, which is the cheaper version. You're going to scoop some of that together and put it in the mixture container. Then you're going to take some of the grade A coffee, which is the more expensive coffee, and you're going to take some of that and put it in the mixture. You're going to mix it all together. And I want this mixture to be $7 per pound. Now, if I wanted to estimate the answer, if I were to split these 50 pounds and 50 pounds apiece, I know that that's not going to be the answer because the mixture has to be $7 per pound, which is not halfway in between those two numbers. It's closer to this variable here. So that means I'm going to need more of the grade B and a little less of the grade A, since I want the mixture to be a little bit cheaper than more expensive. So I'm going to need more. So I'm going to make this maybe 60 pounds to 40 pounds. It's just going to be my estimate. Okay. All right. So let's keep going. Let's make an equation out of what our information is up here. And let's see if we can now solve this. Since there's no difference in any revenue between selling the grade A and grade B coffee, we're simply just going to make a equation using what we have up here. We know that we are going to make in revenue $5 times however many grade B coffee pounds we sell. So $5 times every pound of grade B coffee. Okay, that's how much it's going to cost to make the mixture. Plus, it costs $10 for the grade A, and we designated the grade A coffee as 100 minus C. Okay, so again, this is the grade B coffee, this is the grade A coffee here. So we're going to make $5 for every pound of grade B coffee, plus $10 for every pound of grade A coffee. And we want those two costs to come out to $7 times 100 pounds total of the mixture. So this is going to be our equation to use. Let's simplify. Let's go ahead and distribute and let's simplify. 5C plus 1,000 minus 10C equals 7,000. So let's combine the C's. This makes negative 5C. At the same time, I'm going to go ahead and subtract this 1,000 over to the other side. So that's going to give me negative 5C equals 6,000. Let me continue. Next, I'm going to do, in order to solve for C, the next thing I'll do is I will divide both sides by negative 5. I just noticed I made a small error. 7 times 100 is only 700. My apologies there. So 700 minus 1,000, let me correct my paper there. 700 minus 1,000 is actually negative 300. Okay, so we have an equation, negative 5C equals negative 300. So when I divide both sides by negative 5, I get C equals 60. Oh, wow, look at that. That was exactly what I estimated. I had no idea what the answer was going to be. And that makes me feel really happy that that matches exactly what I thought my answer, my estimate was going to be. So the grade B coffee, we're going to need 60 pounds of the grade B coffee. So let's go ahead and answer the last part, which is the question. We will need 60 pounds of the grade B coffee, and that means 40 pounds of the grade A coffee. Okay, very good. Glad we fixed that. See, we all make small errors. The point is trying to figure out what those errors are and going back and correcting your mistakes, which is important. Okay, let's try another one. Let's move on to the next page. We have, I think, 2 more examples, maybe 3 more examples. Okay, this one deals with uniform motion. Okay, your sister runs at an average speed of 8 miles per hour. 2 hours after Tanya leaves her house, you need to catch Tanya to tell her an important message. You leave in your car and follow the same route. If your average speed of your car is 40 miles per hour, how long will it be before you catch up to Tanya? And how far will each of you then be from your home? So let's first ask the question, what are you trying to find? Well, let's look at the very last part, which is the last question right here. It says, how long will it be before you catch up to Tanya, and how far will you be from your home? So there's two questions. So we're looking for the time it takes for the car to reach Tanya. We're also looking for how far is that? So we're looking for the distance when they meet. Okay, so we're looking for both parts. We got to answer both questions at the very end of this problem. So let's first start by representing a variable of what we're trying to find. The very first thing we're trying to find is the time that it takes for the car, see the car here, to reach Tanya. Okay, Tanya's already running. So she's already, 2 hours ahead of me. And then I'm going to start driving. And by the time they catch up to each other right here, how long has that been? Obviously, it's going to be 2 hours plus some extra time because she's already been running for 2 hours before I start driving. So I know my estimate's going to be over 2 hours. So I'm looking for the time t that it's going to take. So t is going to be the time in hours that it takes for the car to reach Tanya. Okay. When this occurs, the total time that is elapsed is going to be whatever this time is here, plus the original 2 hours that she already was running earlier. So let's look at the facts of this particular problem, right? The facts, what do I know? Well, I know that Tanya was already running 2 hours before the car starts. Okay, I also know that Tanya's rate, so I'm going to put Tanya's rate was 8 miles per hour. And I know that the rate of the car was 40 miles per hour. Okay, so let me put all of that information into a table to be able to help us. So Tanya's rate was 8 miles per hour. The car is going 40 miles per hour. Now, Tanya has already been on the road for 2 hours, plus the time that it takes between where I start and the time to which we meet. Okay, so the total time here is going to be 2 hours plus the time that in between where she is already at the point where I start and when we finally meet up. So me in the car, it's going to take me a total of time t hours in the car, but for her, it's going to be 2 hours plus that additional time. Distance, if you remember the formula from the first page of this lecture, distance is equal to rate times time. Well, we've got rate and we've got time, so therefore distance is going to be rate times time. So what we can do now is we have an expression for distance for both Tanya and me in the car. Now, if I were to estimate what this answer would be, if I look at the distance here in the picture, if that's 2 hours, it's probably not going to take me much longer to catch up to her since I'm traveling, 5 times as fast as she is, right? So if I were to guess, I'd guess maybe a total of 3 hours. And again, I have no bearing other than just using my common sense to coming up with that answer. I don't think it's going to be 10 hours, right? I don't think it's going to be less than 2 hours because she's already been on the road for 2 hours. It's not going to be negative, but it's not going to be really large. It's going to be something a little bit larger than the 2 hours that she was already running on the road. Okay, so let's finally make an equation. Now, when we get to this point, here's Tanya and here's the car. And they are both the same distance from the house. So at this point, when they meet each other, they are both equidistant from the house. So Tanya's distance and the car's distance should be equal to each other. So what I'm going to do is I'm going to set both of these distances equal to each other in my equation. And then I'm going to solve. So let's distribute the 8. This becomes 16 plus 8t equals 40t. Let's subtract 8t from both sides. That gives me 32t. Then divide by 16. When I divide by 16, I get 2. So t is 2. But remember, t represents the time that it takes in total for the car to catch up all the way to where Tanya is. So t is the time that the car is en route. Oh, I'm sorry, I did another mistake, didn't I? This would be divided by 32 on both sides. 16 divided by 32 is in fact 1/2. My apologies there, another mistake. So if t is 1/2, right? If t is 1/2, does it make sense, right? It does make sense, because if the car was traveling already to where Tanya was before, that took her 2 hours by running. It's only going to take another 1/2 hour before the car reaches her. So a total of a 1/2 hour of time for the car, but 2.5 hours for Tanya. So the total time that it takes is a 1/2 hour for the car and Tanya to meet. Now, there was a second question, okay? It says, how far will each of you be from home, right? How far will each of you be from home? Well, remember that the distance from home, I could put it into either of these equations, I'm going to get the same answer. So if I put a 1/2 hour in here for the car, if the car travels 40 miles an hour for a 1/2 hour, that means the car is 20 miles from home. It should be the same for Tanya. If Tanya travels 2.5 hours, 2.5 times her rate of 8 miles an hour, 8 times 2.5 is 20 miles from home. So down here, I would say we will be 20 miles from home. All right, 2 more. Let's go ahead and do those last couple problems here. Now that we know how the steps will work, let's look at one more uniform motion problem. Here we've got a motorboat that heads upstream a distance of 24 miles on a river whose current is running at 3 miles per hour. The trip up and back takes 6 total hours. Assuming that the motorboat maintains a constant speed relative to the water, what is its speed? So what are we being asked to find? We're being asked to find the speed, okay, the speed of the boat. So we're looking for the speed of the boat, okay? So we're looking for speed of the boat. All right, so now we're going to define our variables, okay? So we're going to let R equal the rate of the boat. Now the boat is going at a constant speed. So regardless if it's going upstream or downstream, the boat's power is going the same. Now it's going to appear that it's going faster or slower if you're standing on the shoreline, because the current is either helping it or hindering it with its current of the water. But the speed or the motor horsepower is going to be consistent at a particular rate. So what are the facts that I know, right? I know that the motorboat heads upstream 24 miles. So I know that the total distance is going to be 24 miles. So in a picture, right, if we're looking for, if here's the river, And now I'm going to show this as the river is moving. This is what we're going to call upstream, okay? Meaning the current is helping me upstream. Now, if I'm showing my boat, okay, this is a really rudimentary kind of a boat. And if I show it going upstream with the current, it takes a total of 24 miles to get from here to the end. What else do I know? I also know that the trip up and back takes 6 hours. So I know also that the total time is going to be a total of 6 hours in total. I also know that the rate of the current of the water itself, I'll do this in blue, which represents the water. I know the water, the rate of the water going upstream is 3 miles per hour. So when we're going back, that's obviously going to be negative, okay? So when I'm looking at a table and trying to put all this information together, I know that the total distance is 24 miles, regardless if you're going upstream or downstream. It's 24 miles upstream and then the same 24 miles to come back. I know, oh, excuse me, I put that in the wrong spot, 24 and 24. I know that the rate going upstream is going to be the rate of the boat plus an additional 3 because it's helping me. It's helping me go in that direction. So I'm going to do R plus 3. And then back is going to be R minus 3 because when we're coming back, I've got the current that is hindering me. I'm working against the current on the way back. Okay, so on the way there, my rate is going to appear to be going 3 miles per hour faster than the boat actually is going. But on the way back, it's going to be appearing that I'm going 3 miles per hour slower than the boat is actually going. Now, if you remember again from the first page, we designated time as being distance divided by rate. So I've got distance right here, which is going to be 24 divided by rate. And for downstream is going to be the same 24 divided by the new rate since I'll be going slower. So can we estimate the answer? Okay. If I wanted to estimate how fast the boat was going, just a rough guess, boats could probably go similar speeds to what cars do, right? So it's a motorboat. It does have a motor. You're not paddling, so you're probably going more than a couple miles per hour. So if I were to just make a guess, I'm going to guess something around, I don't know, maybe 10 miles per hour. Okay, just a guess. I have no bearing on whether that is right or wrong. It could be as high as 20, 30, 40 miles per hour. But it's definitely not negative, and it's definitely not more than 80 miles per hour. Boats generally don't go that fast. So I'm limiting it to a number somewhere between a couple miles per hour and maybe 60 miles per hour or so, just to get an idea. Now let's make an equation based on this. Remember, I know the time that it took to go there and back, the total time was 6 hours. So the trip up plus the trip back is going to total 6 hours. So to make an equation, I would set the time to go upstream plus the time to go downstream is going to equal a total of 6 hours. Now to solve for this is a little bit tricky, right? To solve for this, the first thing I'm going to do is get rid of all of those denominators. So what I like to do is I like to multiply both sides by the denominators to get rid of them. So I'm going to multiply this side by r plus 3 and r minus 3, and also do the same thing on this side. So when I do that, you're going to see, when I multiply both sides by r plus 3, r minus 3, you're going to see that these will all cancel. So I'm left with 24, okay, times r minus 3 plus 24. Since the r minus 3 is canceled, you're left with still an r plus 3 equals 6 times r plus 3, r minus 3. So I no longer have any denominators. That's the goal. So let's go ahead and distribute everything and then solve. So this becomes 24r minus 72 plus 24R plus 72 equals 6 times R squared minus 9. Let's go ahead and distribute. That's 6 on the right-hand side. So this is 6R squared minus 54. On this side, the 72s will cancel, so I'm left with 48R equals 6R squared minus 54. Now let's make this a quadratic, okay? I'm going to make this a quadratic. So I am going to solve this for R. So we have 6R squared. I'm going to subtract that 48R over to the other side. And then I can factor and solve. I'm going to pull out a 6. And then factor this into two binomials. So I'm going to have minus 9 and plus 1. So that means the R could either be 9 or negative 1. But remember what R stands for. Let's go back to the original equation. What does R stand for? What did we set R equal to? R is the rate of the boat. The rate of the boat cannot be negative. So that means the rate of the boat must be 9 miles per hour. The rate of the boat must be 9 miles per hour. Okay, let's try one more problem. One more problem. Okay, this last one deals with how long it takes to do a job. So at 10 a.m., Danny is asked by his father to weed the garden. From his past experience, Danny knows it usually takes him about 4 hours to do this job alone. Ugh, he's got a golf time at 1 p.m. Obviously, he won't be able to make it. So Danny devises a plan. He offers to take his little brother Mike with him and his friends to go golfing if Mike helps him with the garden. Mike usually takes 6 hours to do the job alone when it's his turn. He's a slowpoke. So will they be able to finish in time to make their golf tee time if they work together? So what is being asked to find? So that is the question. What are we being asked to find? Will they be able to finish in time to make the tee time? So we're looking for the time it takes to do the job together. So we're looking for T. So we need to define what T is. Okay, we're defining that variable. Let's list all the facts, okay? The facts. We know Danny alone takes 4 hours. We know Mike alone takes 6 hours. Okay? He wants to get this job done in only 3 hours. So we're trying to combine these two efforts together so he can get this done within that 3-hour period. Okay, remember, Mike is a slowpoke, so we've got to make sure that we can combine these efforts. So let's figure out what we can do. Let's draw a picture. In this case, I think a table would be most useful. Danny, it takes him, again, 4 hours to do the job alone, which means in just 1 hour, he can finish 1/4 of the job. Mike takes 6 hours to do the job. So that means in just 1 hour, he would only finish 1/6 of the job in an hour. So together, hours to do the job is going to take T. That's what we're trying to find. We're trying to combine their efforts into the time it takes to do the same job, but by combining their efforts. So obviously this will be 1/T. I don't know what the rate is of them combined, but if I found it, I could find the time it takes to do the job together. So what I'm going to do is now I'm going to estimate my answer. Obviously, if it takes Danny 4 hours alone, but Mike 6 hours alone, and if Mike helps Danny, it's going to take less than 4 hours. So if I were to guess, maybe around 3 hours. It's not going to be half because Mike is slower, right? So somewhere between 2 to 3 hours. I'll just guess around 3 hours. It's not going to take more than 4 hours because they're working together, but it's certainly not going to be close to 0. So I know it's going to be somewhere between 2 to 4 hours to get a better estimate. So if we wanted to make an equation of this in order to solve it, we set the parts of the job done in 1 hour as a sum in an equation. Okay, I know Danny can get 1/4 of the job done in an hour, and I know Mike can get 1/6 of the job done in 1 hour, but I know working together, they can get 1/t of the job done in an hour. So I need to combine these together in order to figure out what t is. So that's it. Now I just have to solve for t. So again, always get rid of fractions. So I am going to multiply both sides by the common denominators that will get rid of the 4, the 6, and the t, and that's going to be 12t to both sides. So when I distribute that 12t, see 12 and 4 reduces to 3t, 12 and 6 reduces to 2t, and then t over t cancels and you're left with 12 on the right-hand side. So I have 5t equals 12, and when I divide both sides by 5, I get t equals 12 over 5, which is 2.4. So to answer this question, in order for Danny and Mike to weed the garden, they can finish the job in 2.4 hours. So yes, they can make the tea time.